Hello, friends. Welcome to Hydraulics and Hydraulic Machines class. In this lecture, we discuss on some of the problems related to Kaplan turbine. So, in the last class, we have done some problems on Francis turbine, and now we will go with the Kaplan turbine. So, in today's lecture, the topic is problems related to Kaplan turbine. That is what we will take it up. So there are two types of problems in Kaplan turbine, but anything is the formula are same for any of the things. So let me take into the first problem. A Kaplan turbine, a Kaplan turbine develops 22,000 kilowatt at an average head at an average head of 35 meters. Assuming a speed ratio of 2, flow ratio of 0.6, diameter of bus equal to 0.35 times diameter of runner, and overall efficiency of 88%. Calculate the diameter, speed, and specific speed of turbine. So given is tapped power P is equal to 22,000 kilowatts. Head H is equal to 35 meters. Speed ratio Ku is equal to 2 and flow ratio Kf is equal to zero point 0.6. Diameter of boss dB is equal to 0.35 times the diameter of the hub of runner. So diameter of boss, this is dia of runner. And what he has other things. Otherwise, that means dB is equal to 0.35 times d0. This is next thing. Overall efficiency is equal to 88%. These are the data. So from the given thing, actually, the first thing what we try is how to find the diameter of runner, dia of runner. This is our first objective. If this is the first objective, dia of the runner, what is the equation for us? It is Q is equal to pi by 4 into d0 square minus db square into, this is area, into velocity of flow. This is the solution. So in this uh, Q is, now we have to calculate, VF is to be calculated. So that's why, given the speed ratio and flow ratio, let us try first what is the things. So given this, U is equal to U1 is equal to KU speed ratio into 2GH. So that is 2 into square root of 2 into 9.81 into H is equal to, how much is the H? 35 meters. So that amounts to 52.4 meters per second. Then similarly, VF1 is equal to KF into root 2GH. So that is equal to, KF is equal to zero point 0.6 into 2 into 9.81 into 35. That amounts to basically 15.7 meters per second. So VF1 is obtained one. Then Q, you all know that the only way to get Q is going for overall efficiency. Overall efficiency is equal to P by gamma QH, or Q is equal to P by gamma H into ton. So P is equal to 22,000 kilowatts actually. 22,000 into 10 to the power of 3 divided by 9810, H is 35. Then eta 0 is equal to, how much is the thing? 0.88, 88%, that is 0.88. So all this works out to 72.8 meter cube per second. So please remember, Q is there, PF1. Then let us go into that equation. So 722.8, that is Q. So what is the equation for us? Q is equal to basically pi by 4 into d0 square minus db square into VF1. So therefore Q is equal to 72.8 is equal to pi by 4 into d0 square minus db is equal to 0.35 d0 whole square into VF1 is equal to the 15.7. So now you see the whole equation. If I just simplify it, so how much we are going to get? This is 72.8 is equal to pi by 4 into 1 minus 0.35 basically square, right? Into d0 square into 15.7. So finally, calculating from this, d0 is equal to 2.6 meters. So therefore, db is equal to 0.35 times 2.6 meters. Right. Then what is the next question? Speed of the turbine. Speed of the turbine is equal to U1 is equal to pi into D0 into N by 60. So that means basically N is equal to 60 into U1 by pi D0. Already U1 we calculated. What is that U1? 60 into 52.4 divided by pi into D0 is 2.6. So this amounts to 384.9 RPM. This is first thing. And there is one more question also there. Specific speed of turbine.
n root p divided by h to the power of 5 by 4. So if I take it, it is equal to 384.9 into root is equal to 22,000. It is always should be expressed in kilowatts only. H is equal to 35 to the power of 5 by 4. Then this will represent 670.6. Basically, this is the specific speed. So the second problem in Kaplan turbine we are dealing with at present. The second problem is the following data. The following data pertain to pertain to a Kaplan turbine. Power available at shaft. Power available at shaft P is equal to 22,500 kilowatts. Speed N is equal to 150 RPM. Dia of hub is equal to 2 meters. Hydraulic efficiency is equal to 95%. Overall efficiency is equal to 88%. Outer diameter of runner outer diameter of runner, that is D naught, is equal to 4.5 meters. Assume the turbine discharges without will. Without will. The meaning of without will is the discharge is radial. Without will at exit. Determine the runner vane angle at hub and outer periphery. So we need to determine the runner vane angles at hub and outer periphery. This is what we need to find out. So let us go into the problem. So a new problem actually. So vane angles determination. So for vane angles determination, first let us say what he has given. You have seen the data also. So naturally, I will go with the first thing is data Q determination. And Q determination is only possible with only one equation, that is eta 0 is equal to P by gamma QH. So eta 0 is equal to, already he has given eta 0 is equal to how much actually overall efficiency. 0.88 is equal to P is equal to 22,500 kilowatts into watts. If you convert, it will be 10 to the power of 3 by gamma is 9810 Q into H is equal to, he has given the head as 20 meters. So in the problem also, if I don't know, head is equal to 20 meters, right? Taking that. So now except Q, everything is known. So find Q. Find Q. So Q is equal to how much it will be? Please tell me. 22,500 into 10 to the power of 3 divided by 9810 into 20 into 0.88. So that amounts to 130.32 meter cube per second. So one answer is obtained. So once that is known, we know that what is the relation. Q is equal to pi by 4 into d0 square minus db square into Vf1. So already D0 is given. So Q is equal to 130.32. It is equal to pi by 4. D is equal to how much they have given? 4.5 square minus 2 square into Vf1. Therefore, Vf1 is equal to Vf1 is equal to 10.21 meters per second. So this is the second calculation. After Q, this is the second calculation. So VF1 is also obtained. Now basically what he is asking, a question is, what are the vane angles? If you want to go into the vane angles, you need to know what is U also. So what is the equation for U1 is equal to pi d0 into n by 60. So it is equal to pi into d0 is 4.5 into n is equal to 150 divided by RPM 60, this by 60. So naturally we are going to get 15.7 meters per second. So this is the second. So now if I substitute it, now when with the vane angles, then I need to know VF1, I need to know VW1. How I get VW1? The VW1 is the only equation is hydraulic efficiency equation. VW1 U1 by GH. So hydraulic efficiency, how much they have given actually for us? 0.95. So hydraulic efficiency 0.95 is equal to VW1 into U1 is 15.7 divided by 9.81 G, and H is equal to 20. Therefore, VW1 is equal to how much? So VW1 is equal to, if you calculate, it is going to get 11.87 meters per second. Right? Now this is the thing which we got it. So if I take the basically the vane, suppose the vane actually, this is the vane. Right now how it will be, suppose for example, so this is how v1 is going to be, because the velocity triangle when you are drawing it you should always be clear. So this is the u1, right? Then actually this is vr1, and this is the vf1, vw1. You can ask me generally, sir, normally what you are writing is this is V1, this is U1, this is VR1. Then this is how actually you are writing, this is VF1, this total is VW1. This is what you are drawing regularly. But why you have gone like this? So, right? So then the question is, now you see what is here, if you see, VW1 is always greater than U1. That is the thing. But in this particular problem, I got the answer such that VW1 is equal to 11.87, whereas U1 I got it as how much? U1 is 15.7 actually. So naturally, if this is the case, what should I do? So VW1 is less than U1. That's why this diagram has come. Otherwise, the diagram is only this only. But because this VW1 is less than U1. Here, if you see, this VW1 is less than U1. That's why I have drawn like this. So, you know, the angle made by V1 with horizontal is alpha, whereas the angle made by this is what we call it as the VR1 with horizontal, which we call it as theta. This is the general process. That's generally we do it. Whatever VR1 makes with the horizontal is what we call it as theta. Why only this side? Why not this side? The basic problem is the direction. If you see it, where you can get it. So V1 is this, U1 is this, so VR1 is this. So that's why it has to be this angle only, right? So this is a new peculiar thing that you should understand, but not much change it will make. So from the inlet velocity triangle, if you take it, suppose what will be this angle? This is 180 minus theta. So therefore, for example, if I take tan 180 minus theta from inlet velocity triangle is equal to Vf1 divided by this total is what actually total is u1 and this minus v, so it is u1 minus bw1. So if you to do it, vf1 is how much value you have 10.21, whereas u1 is how much, it is 15.7 minus 11.87. So this is what we will get it. So from this, so tan 180 minus theta is equal to, if you do the thing, you are going to get 2.26. Therefore, 180 minus theta is equal to tan inverse 2.26, which is equal to, basically this will be 69.4 degrees. Therefore, theta is equal to 110.6 degrees. So this is what you should understand in this. So this is the only difference that which we should know, because the values you should see, because these two values, based on that you should draw it. Suppose if you do it same like this, if you draw it, then vw1 is less than u1 actually. So that is why I put like this. Then coming to the next, actually, outlet velocity triangle, if you take it, outlet velocity triangle, already they have mentioned actually it, the triangle, it is in such a way actually, the outlet velocity triangle is, this is what we call it as VR2. It will go like this, and then this is what I call it as U2, right? And this is what we call it as VF2. Okay, so this is the thing. So in the outlet velocity triangle, like every time whatever we draw, so this is VR2, fine. This is U2, right? And this is basically what I call it as VF2 is equal to V2, and VW2 is equal to 0, and this beta is equal to 90 degrees, and this is phi. So outlet velocity triangle tan phi is equal to Vf2 divided by U2, basically. So that we can write. So it is nothing but Vf1 divided by U1. Vf1 is 11.10.21 divided by U1 is 15.7. So naturally it is equal to 0.6503. Therefore, phi is equal to 33.03 degrees. This is the second answer. So it's a peculiar problem which I have taken up in this particular Kaplan turbine. With this, the Kaplan turbine topic is over. So we will take up in the next class another topic, and then we will go forward. So I will stop this my lecture here in this, and so that we have done all the problems also in the Pelton turbine, Francis turbine, and Kaplan turbine also. Kindly work more on that.
Like, share, and subscribe. Hit the bell icon for more updates.